Hi everybody. The beginning of this is intended to be a recap of what we hopefully got to in class today. So we should have by now done the investigation with the string and the push pins and drawn our ellipse and learned the definition of an ellipse, that the definition of an ellipse is it's a set of points where at any point on the ellipse the sum of the distances to the two foci of the ellipse is constant. So if I call this D1 and D2, D1 plus D2 is always constant no matter where I am on the ellipse. So for any point on the ellipse, if I do this, D1 and D2 is equal to D1 plus D2 wherever I am on the ellipse. So that was the investigation and the definition of an ellipse. And now we have just some kind of formalities. We have the equations for an ellipse, which are very similar. An ellipse centered at 0, 0. Very similar to what we saw with a circle. Okay, but you'll notice that ellipse equations are always set equal to 1. Okay, and we have some information about the axes of the ellipse in the denominators of our fractions. So this information here is important. A is the distance from the center to a major vertex, so let's label that right here on our diagram. Right, so this whole thing here is what we would call our major axis. Right, so this is a major axis. And then on this ellipse here, the vertical ellipse, the major axis is the longer one. Okay, they're both, it's always the longer one, major axis. And then the shorter one is called the minor axis. Right, so these two are called the minor axis. And we label A as the distance from the center to the major vertex. Oops, so A is like this distance here, A, and B is this distance here. Okay, and then on the vertical ellipse, A is still, right, it's basically half of the vertical axis, and B is half of the minor axis. Okay, and then another important relationship that we're going to use when we start doing some of the examples is that c squared equals a squared minus b squared. You don't have to worry too much about the derivation of that. It requires a whole bunch of crazy algebra. We can just accept the formula. It looks a little like the Pythagorean theorem. It does have to do with the Pythagorean theorem, but obviously it's not exactly the Pythagorean theorem. But for now, we could just accept that the square of the distance from the center to the foci is equal to the difference between a squared and b squared. And the foci aren't on these diagrams here, but if they were, they'd be like roughly like here and here, right? And maybe here and here. Okay, so the foci are those points that that basically held the string today taught. That allowed us to draw the ellipse. And so the distance C is this distance here from the center to one of the foci. Okay, I think the only other things to label here would be what we call the vertices and the co-vertices. Okay, so the vertices of the ellipse are the endpoints of the major axis. Okay, so these are vertices. And then this is a co-vertex here, which are the endpoints of the minor axis. Okay, so on the vertical ellipse, this is a vertex here, and this is what we would call a co-vertex. Okay. Most of the time when I ask you for the vertices, identify the vertices of an ellipse, I'm actually expecting all four of them. You don't really have to distinguish between the vertices and the co-vertex, but just know co-vertex just in case, or co-vertices just in case I use the term. Okay, so here's some examples, and I'm going to write that formula c squared equals a squared minus b squared up here, just so that we remember it, because we're going to need it in some of these examples. Okay, so these first four problems all ask us to identify the center, foci, and vertices of each ellipse and then graph it. Okay, and every one of them kind of gets gradually more difficult. Okay, this is an ellipse right here. This ellipse is in the most standard form it could possibly be in. This one has a center at 0, 0. Okay, again, similar to the circle, right? If it wasn't at 0, 0, we would see some translation happening with the x and the y squared. Okay, so this center is at 0, 0. And sometimes, personally, it's easier to actually, look at the equation and draw it first before I try to figure out what the vertices and the foci are. You could kind of do it either way. You could figure them out first and then draw it, or you could draw it first and then figure it out. This 49, right, this is our a, right? So a squared equals 49, so that means that a is going to be plus or minus 7, really, right? So that means we're going in the x direction, because the 49 is under your x squared. In the x direction, we're going 7 units to the right and 7 units to the left on one of our axes here. And then in the y direction here, we're going to be, so this is saying that, this is telling us that b squared is equal to 36. Okay, and a is always the larger of the two. That's just by convention. So that means b is going to be plus or minus 6. So in the y direction, we're going up 6, oops, and down 6. Okay, so we can clearly see our vertices here are 0, plus or minus 6, and plus or minus 7, 0. Okay, you could write them like that, or you could write it as 4 separate points. That's up to you. And then if I was going to draw the ellipse, it's just going to look like a smushed circle. This one is pretty close to being circular, though, because the a and the b value are only 1 apart, so this one is pretty close to being circular. Okay, so now the foci are not as clear. The foci, that's where this formula comes in up here. Okay, so we have a squared and b squared, and we're going to need it to find c. So c squared is going to equal a squared minus b squared. So we already know that a squared is 49 and b squared is 36. So c squared is equal to 13, which makes c equal to plus or minus the square root of 13. So that's a little ugly. It's a little bit difficult to graph, but that's going to give us our foci. And we know that our foci are going to be along the x-axis, because that is our that's our major axis. Okay, so your foci are always along the major axis. So the square root of 13 is, I don't know, it's between 3 and 4, right? 3.6. So we'll take 3.6, we'll put one focus here, and one focus here, right? And we can call it F1 and F2. It's not really necessary to label it, but just to remind us that those are foci and not vertices or anything like that. And just to be formal about it, we will indicate our foci as the ordered pairs plus or minus radical 13, comma, 0. I'm going to make those blue just so, to be consistent. Okay, and that's that one. All right, I don't remember if the next example, next example is right below here. Okay, so this one's looks a little different, right? Because the center, hopefully we could see the center is not 0, 0 here. So just like with the circles, ellipses, will translate their centers the same way a circle will translate its center. So the center of this guy is at 3, -2. Hopefully we can see that pretty easily. So 3, -2, I'll plot my center right there. Okay. And again, sometimes it's easier to actually go ahead and graph it first rather than try to identify what the vertices are first. Okay, so we have our a squared value here, right? So we have a squared is equal to 4, which is going to give us a equal to plus or minus 2. Now, that's not, plus or minus 2 are not the vertices of this necessarily, or the covertices of this. Plus or minus 2 is telling us how far we're moving from the center, right? So this is distance from center, right? So we're going, and this is again along x. Right, along the x-axis because it's underneath the x. So we're going 2 units from the center along the x-axis to the right and to the left. Okay, and then likewise we have our b squared value is 64. So b is plus or minus 8. So we're moving 8 units up. This is on the y-axis, 8 units up. This is going to bring us to there. And 8 units down, looks like we're going to run out of room, so I'm going to have to make a 9 and a 10. So it's like down here somewhere. Okay, and then we can draw our ellipse, and this is a much more elongated ellipse than the last one we had because the axes are so much different here. So in this case, we have our major axis is vertical, is going up and down. Okay, so our vertices we could see just by looking at it, right, are 5, -2, right, so 5, -2, 1, -2, and 3, 6, and 3, -10. And you should see a relationship here, right? We have, right, our vertices, we have 2 vertices that are in line, with our x value of our center, and notice that -2 is 8 units from 6, -2 is 8 units from -10, right? So that's where that that square root of 64 comes in, 8 units. And then likewise here, -2, these -2s align with our y value, so we have 3, 5 is 2 units from 3, 1 is 2 units from 3 in the other direction. Okay, so and again, for the foci, we're going to need to use our c squared equals a squared minus b squared, keeping in mind that a is always our bigger value. Okay, so c squared is going to be 64 minus 4, which is 60. So that makes c plus or minus the square root of 60, which if I simplify that, I get plus or minus the square root of 2 square root of 15. Okay, because 4 is a perfect square factor of 60. So plus or minus 2 square root of 15. So what does that mean? Okay, that's telling us that the c value, meaning c again being the distance from the center, right? So it's measuring this distance here. Okay, the distance between the center and the focus is 2 root 15. Okay, so let's think about that. What that's telling us is that our focus is going to be the x-coordinate will be 3, and the y-coordinate will be the center plus or minus that 2 root 15, right? So the center, that -2, if I take -2 and I add 2 root 15 to it, I'm going to be up here somewhere. If I take -2 and I subtract 2 root 15 from it, I'm going to be down here somewhere. Okay, so my foci are at 3, comma, -2 plus or minus 2 root 15. So again, that's 2 points. Okay, and we could roughly figure out what that is if I use my calculator. -2 plus 2 root 15 is about 5.7, so that's actually pretty close to my vertex there. And then -2 minus 2 root 15 is going to be -9.7, so again, pretty close to to my vertex there, which makes sense, right? So the more elongated the ellipse is, the further apart the foci are, or the closer to the vertices the foci are. All right, let's see what's next. Okay, so this is an equation of an ellipse in yet a different form. Okay, keeping in mind that the equations of an ellipse, in order to graph them, they have to be set equal to 1. Okay, so it's relatively easy to set this equal to 1. We can see that we can divide, if we divide the whole thing by 225, we'll get equal to 1. But now we have to figure out 25 over 225. You want to simplify the fraction. You don't want to do the division and then get a decimal. You want to simplify the fraction. So 25 2/25, or 25x squared over 225 is the same as saying x squared over 9, because 25 goes into 225 9 times. Okay. And the 9y squared over 225 is going to be y squared over 25 equals 1. Right, and now this looks just like the first one we graphed, right? So now it's in a form that we're familiar with, and like I said, it looks exactly like the first one we graphed. This is an ellipse with a center at the origin. It has a horizontal axis that goes from -3 to 3. Its vertical goes up to 5 and down to -5. And then we could draw it. Okay, so our vertices in this case are plus or minus 3, 0, and 0, plus or minus 5. And if we were going to find our foci, still c squared is going to be equal to a squared minus b squared. In this case, a squared is 25, b squared is 9. So 25 minus 9 is 16. So c is going to be really 4 units from the center, right? So we're going to be going up 4, down 4, and there are our foci. So our foci are at 0, plus or minus 4. Okay, so once we have that set equal to 1, that's a pretty easy problem. Okay, the last one here is the trickiest. And this is one of those situations like when we did with circles, where we have to complete the square, okay, in order to write it in a form that we recognize. We're going to be doing a lot of completing the square. So, we spent a little time in class on it today, and you're going to be seeing it pretty much for every conic section we do. So I'm going to do this where I have plenty of room. So I'm going to complete the square. First, I am going to rearrange so that I have my x's together and my y's together, and then I have all my numbers on the other side. So I've got x squared plus 6x, and then I'm going to leave a little space here. And then I have plus 9y squared minus 90y. I'll leave a little space here too. And I'm going to move the 225 over, because that 225 doesn't look like it's going to help us complete any squares here. And even if it did, it's a good habit to just kind of move all the numbers over and then deal with them later. But if you do see that one of the constants helps you complete the square, then you can leave it. Okay, so to complete the square on the x's, on the x squared plus 6x, again, remember that we're taking half of this value and squaring it. Right, so half of 6 squared, half of 6 is 3, square it is 9. So we're going to add 9 here, but because we added 9 on the left side, we're going to have to make sure that we add 9 on the right side. And now, a little bit trickier here, because we can't complete the square if we have a leading coefficient. Right, so we're going to have to rewrite this guy. All right, and we're going to rewrite this as 9 times y squared minus 10y plus something. Okay, and so now we can complete the square. Again, you should remember this from algebra 2. We can complete the square right here on this. Right, y squared minus 10y, if I take half of 10, it's 5. And I square that, I get 25. But now, when I add, what did I actually add on the left side? I actually added, remember, 9 times 25 on the left side. So that means I'm going to have to add 225 over here in order to balance that out. Okay, so now if I rewrite, I have x plus 3 squared, right, I'm factoring, right, plus 9 times y minus 5 squared equals, those 225s are going to cancel, equals 9. Okay, still not a form that we can graph. Okay, we still need to rewrite it in a form that we can graph. So we don't, over here, we don't want it to be a 9, we want it to be a 1. Right, so we can divide this entire equation by 9. And we have our equation x plus 3 squared over 9 plus, the 9's are going to cancel here, so we have y minus 5 squared. And I'm just going to write it over 1 just to remind me that there is that value down there, equals 1. Alright, so I'm going to actually rewrite this equation up here so that we can see it and use it. X plus 3 squared over 9 plus y minus 5 squared over 1 equals 1. Alright, so our center now, again, this looks like the second example we did. So it was a lot of work to get there, but it looks just like the second example we did. Our center is at 3, negative 5. So 3, negative 5. And now I can use my a and my b values. So my a value here is, my a squared value is 9. So that means that I'm going 3 units to the left and right of my center. And then my b value, my b squared value is 1. So that means my b value is 1. So I'm going 1 unit up and down. And here's my ellipse. Alright, so my vertices are 3, negative 4, 3, negative 6, which again makes sense, right? Because we're at an x value of 3, just like the center is at an x value of 3, and then negative 4 and negative 6 are both 1 unit away from negative 5, and that's what this 1 here is indicating. Right, and then my other vertices are 0, negative 5, and 6, negative 5. So again, should make sense because that negative 5 is coming here from the center, and the 0 and the 6 are both 3 units from the center, and that 9 is telling us that we're going 3 units from the center in the x direction. Okay, and now my foci, we're going to use our handy formula, c squared equals a squared minus b squared. A squared is 9, b squared is 1, so that means c squared is 8. So c is plus or minus 2 root 2. Okay, so we're going 2 root 2 units from the center in both directions. Okay, so the y coordinate of our foci, we should be able to see the y coordinate of our foci is negative 5, right? Because our foci are going to be along this axis. Okay, but the x coordinate of the foci is going to be 3 plus 2 root 2, so over here somewhere, and 3 minus 2 root 2. So our foci are at 3 plus or minus 2 root 2, comma, negative 5. So again, I can grab my calculator just to approximate where those are. 3 plus 2 root 2 is about 5.8, so it's going to be hard to draw, but, and then 3 minus 2 root 2 is about 0.17. So again, they're really very, very close to the vertices. It's kind of hard to draw those. But here, being able to identify them up here is more important than being able to draw them perfectly, especially when, they're not on well-defined points. All right. So now here's a couple of examples that I'm not asking you to graph, I'm just asking you to interpret the information and write an equation in the standard ellipse form. Okay, so it might help to draw a picture just so that you can see what it looks like. So this first one is centered at the origin. The ellipse is 20 units high and 12 units wide. Right, so we're looking at 20 units high, meaning like this entire thing is 20 units. That's how I would interpret it, at least. And then 12 units wide is, this whole thing is 12 units. Right? So we can see that my a squared is going to be below the y, right? And the b squared is going to be below the x, right? So we're really looking at a and b. So a here, this is a is 10 and b is 6. Right, so we'll write that here, a equals 10, b equals 6, and we centered at the origin, so we end up with something that looks like this, x squared over, okay, again, the b value is going to go under the x squared because the minor axis is on x in this case, so x squared over 36 plus y squared over 100 equals 1. Okay. So the next one, centered at the point 3, 0. So again, even though it's not drawn for you, it might be helpful to draw it. Centered at the point 3, 0. 1, 2, 3. We have a vertex at negative 4, 0. 1, 2, 3, 4. And then we have another one at 3, 5. 1, 2, 3, 4, 5. So one of these is obviously a covertex. This 3, 5 is technically what we would call a covertex. Okay, so this is what like half of the, or a quarter of the ellipse would look like. If I kept drawing it, I'm going to run out of room. But you could kind of see, right, that this is giving you a b value and an a value. So again, this time the a value is along the x-axis because it's the longer one. The b value is right here. So this a is whatever the distance from 3 to negative 4 is, so it looks like 7. And b is going to be the distance from 0 to 5, so that one is 5. So our equation here, we have a center not at the origin, so we're going to have to write that transformation, or that translation, x minus 3 squared over 49 plus y squared. We don't have to write y minus 0 squared. You can, but it's not necessary. Okay, so y squared over 25 equals 1. Okay, last one here. Centered at the origin. Okay, so we got a center at the origin. We have vertices at 0 plus or minus 6, so we have a 6 and a negative 6. Those are vertices. And then it says foci at negative 7, so this is F1 and 7, F2. Okay, so it's telling us foci and a pair of vertices. Really, again, since these are the foci, since the foci are 7 units away from the center, this 6 and negative 6 are technically co-vertices. But again, we don't have to get super technical about that. So this is going to be something out here, right? The other vertices are going to be outside of the foci. So we can tell that this is going to be our a value here, whatever that might be. This is our b value. So remember our handy formula, c squared equals a squared minus b squared. Before, we were using it to find c. In this case, we have c, right, because we know the distance from the center to the focus. And we have b. And we're going to need it. We're going to use those two things to find a, because that's our unknown, and that is what we need to write our equation, right? So again, keep in mind that this distance here is c, okay? So c squared is 49 equals a squared, we don't know, minus b squared is 36, right, because b is 6. And now we're just going to solve the equation. 49 plus 36, so 85 is equal to a squared, right, which means that a is the square root of 85, which is rather ugly. The square root of 85 is a little bit more than 9. This is like 9.2. Okay, but we're not really trying to graph this, so we don't really care what that value is. We just need this a value, right? We really actually need the a squared value to write our equation. I'm going to go down a little bit here to create some room. Okay, so again, keep in mind the a squared is along the x, and we're centered at the origin, so we're going to have x squared over a squared. In this case, that's 85, plus y squared over b squared, in this case that's 36, equals 1. All right, so again, this one will be a little bit of an ugly one to graph because of that 85. We're not going to have very well-defined vertices because we'll have to approximate them, but we can easily write the equation using that formula that we had, the c squared equals a squared minus b squared. Okay, and I think that's it for now. Feel free to refer back to this as you're working on the rest of the problems in this packet.